make it a little bit bigger. So this is a limit at infinity, okay? And it's different than an infinite limit, right? An infinite limit is one where the bottom is 0 and the top is not, right? That's an infinite limit. This is a limit at infinity. So it's what's happening out on the edges of the graph. And you know what happens is you head out this way and as you head out this way. So a couple facts about these limits at infinity. The limit as x goes to infinity of 1 over x is going to be 0. And this is true no matter actually what exponent you have here. So x squared, x cubed, x to the r, as long as r is bigger than 0, this is going to be true. So that turns out to be a useful fact that we really want to use a lot of times when we're working with these limits at infinity. And it's also true if x goes to minus infinity. Turns out either way, you're dividing by a really small number, so this whole thing becomes 0. Now, the problem with your question, of course, is that it doesn't really have that, right? It doesn't have 1 over x to the r. This piece is going to minus infinity, because that's what I'm looking at. X squared plus 4x, it's not entirely clear what that whole thing is doing, but it actually doesn't even matter because I can't add these together, right? Remember, the limit laws normally would allow me to take each of these limits separately, but this limit doesn't exist, so I can't take its limit and then add it to this other value. So I need to do a little bit of work, and what I'd like to do is get some things that look like this, because these limits I know do exist, and then I can start to add or subtract them together. So the strategy or the trick here is that I'm going to multiply top and bottom by the conjugate. And I think one of the things you learn as you do calculus, just kind of ran out of room there, and more math, is that sometimes you just got to do stuff and you're not totally sure how it's all going to work out, right? I think in earlier math classes, that's not an issue, right? You kind of know, like when you're going to solve an equation, you sort of know how it's all going to work out. You just got to go through the details to make it sort of final, right? And see what it ends up being. But in calculus, some of these manipulations, we're not really sure how this is all going to work out, but I got to do something. And so if I multiply by the conjugate, that's going to change it. And it's also potentially going to give me a way of coming up with some of these sorts of fractions. So what I get here is x squared and then minus this, right? X squared plus 4x. That's the way conjugates work, right? You get the first term squared and the last term squared. The middle terms cancel out. And then I have this bottom, x minus the square root of x squared minus 4x. So again, I don't know exactly how this is all going to work out, but I'm hopeful it's going to be better than what I started with. So the x squared and the minus x squared cancel, and that's certainly an improvement. So this may not look all that much better, but it's actually in a much better form. If I'm trying to create these fractions, what I really want to do is I want to divide the top and bottom by x. I have to do the same thing to the top and bottom. I typically pick the largest power in the denominator. So this becomes x divided by x is 1. And here there's a little, this is the little extra challenge here. I want to bring the x inside the square root so I can simplify it. So x is the square root of x squared in most cases. Turns out that's only true when x is positive. But in this case, x is going through negative values. So here's a little trick. I can replace x with minus the square root of x squared. See if you can convince yourselves of that. If I take the square root of x squared, that is always going to be a positive value, right? That's going to be x. So what I need to do here is replace that with a negative value, because I know x is going to be negative. You can try it for like a big number like -10, right? -10 squared is 100. The square root of 100 is 10, but it needs to be negative to make those equal. So that's what I'm going to replace this with.
Does that not apply to the numerator then when we divide by x?
That's right, because the numerator there is just, I'm just dividing by x. So there's no issue with like having to change it, or it's because I changed it to the square root of x squared that I have an issue with that negative. Does that make sense?
Yes.
And that's only true when I have when it's going to minus infinity. If it's not going to minus infinity, then I also don't have to worry about that because there's no negatives to worry about. Okay, so it's sort of just in this one little situation, and it's an algebraic trick. It's not really like a calculus big idea, but it certainly is something you may not have worked with or just thought of before. So this then, well, I should have done that in 2 stages. Let's do it in 2 steps here. For the second part, instead of dividing by x, I'm replacing that with negative square root of x squared. So I get the limit as x goes to infinity of -4/1 plus. These square roots can be combined now. X squared divided by x squared is 1 minus 4/x. Okay, so this is getting good here because the limit laws allow me to take the limits of each of these pieces separately. Okay, the -4, the 1 inside the square root, and the -4/x. And I can do that because each of these limits now exist. That's just going to be -4/1 plus the square root of 1. And this limit is just 4 times that limit, so that's going to be 0. Plus or minus 0. Right, 4/x, 2/x squared, -17/x cubed, those are all going to 0. So this in the end goes to -2. So it's a very good question, and that is no way a straightforward problem, right? That's our sort of most challenging version of these limits at infinity. It's got 2 big complications. One, it has this first step of changing the problem by multiplying it by a conjugate, which is challenging enough. And then secondly, it has this substitution, which is like the other complication. So the good thing is those are pretty much the only 2 complications that you'll get with these sorts of limits at infinity. There's not really any others that I can sort of throw at you. A more general kind of question, or let's say, you know, this one would be a very, I would say, straightforward sort of question. No complications here. This is the limit as x goes to infinity. The strategy is I'm going to divide top and bottom again. I'm going to divide top and bottom here by x squared in this case. I want to divide by kind of the largest power present. So 2x over x squared gives me 2 over x plus 1 all over 3 minus 1 over x plus 5 over x squared. And this is still a limit. I won't ding you if you forget to write that limit there, but of course you got to keep track of it, right? Because the limit is going to make all of these pieces go to 0. Anything that has a higher power of x on the bottom is going to go to 0, and this whole thing is going to end up as 1/3. And you may have already sort of realized that from when you studied this idea in college algebra or pre-calculus course. You wouldn't have used the limit terminology, perhaps. You would have called it a horizontal asymptote, right? But that's really the same idea. This is saying as the x values get larger and larger and larger, the function values get closer and closer and closer to 1/3. In fact, the function values can be made as close to 1/3 as we want by picking x values sufficiently large, right? You can have a delta epsilon definition of this as well. We don't, so don't worry, but you could. Any questions about that example? Okay. Let me check our. Homework here. Okay, so you have let's see, tomorrow. So yeah, tomorrow you have this homework due from 2.6. So covering these limits at infinity. All right. Any other questions from the homework? I can take one of these questions and use it as my lecture, right? Any other questions from the homework?
Hi,
Yeah.
Professor. Hi.
Hi.
Actually, did you do the fourth one? I want to see that one.
The fourth one from the homework?
Yeah. No, from the test.
Oh yeah, I did go through the fourth one. So we could talk about that after class, but I did record a key. So you could look at that recorded key as well for that quiz. So yeah, we'll have to take a look at that separate.
Okay, thank you.
Yeah, yep, no problem. Okay. So as I was saying, just make sure you're keeping up with the homework, that you're on sort of a good routine where you are working through the homework a little bit each day is really the best. Keep asking questions. I'm getting some questions from some of you online, not a ton of questions. I don't know always if that's a good thing or not. It could mean it's going pretty easily, but it could also mean you're not getting it done, or I don't know. So keep in touch with me, right? That way, it's a good way for me to get help to you and also get a sense of kind of where you are. If I get a lot of questions about a certain type of problem, then I can spend some time working through those problems during these sessions, right? And make sure you're getting the help you need, the ideas you need. Okay, so let me just think if there's anything else in 2.6. I think we covered. I think we covered what we needed to there. Just looking, they do talk about, if you look through the section, they do talk about the precise definition of the limit, but that's not, we don't have to worry about that precise definition of the limit. Okay, yeah, I think that's good. The real key there is that you want to divide by x so that you end up with limits that exist, right? Before you divide by x, or x squared or x cubed, you have a lot of infinite limits. You can't add or subtract those infinite limits because you don't know what they will end up being. So dividing by x gives you a chance to see what those limits actually are. A lot of them end up being 0, and then you can calculate that value. So I would say 2.6 is a relatively compact idea of what we are trying to do. Doesn't mean it's always easy, but it's just a couple concepts, right? Some of the chapters have a whole bunch of different big ideas within them. Okay, so let's talk a little bit, introduce a little bit of 2.7, and 2.7 is really where we start to take the idea of limit and apply it to the things that we really care about, right? In some sense, like, who cares about a limit? I mean, we learned how to do some limits, but what is it really doing for us? Kind of not that much, really, right? It's like just telling us what the function is doing, kind of near a point. I guess that's our intuitive idea. Just sort of interesting, but in no way revolutionary, right? So let's take a look here at 2.7. That's a 7. And 2.7 is introducing derivatives. And we didn't, hopefully you watched some of the lecture capture and saw this sort of introduction to calculus. One of our big ideas with calculus is that we'd really like to find this tangent line to this curve at this point. And the tangent line is this red line. Now, why we want to find that, we got a little bit of a hint of that in the 2.1 section, which is this tangent line actually turns into, it's a physical property of this function. So if this function is position, the tangent line is velocity, right? Or there's lots of other physical descriptions that connect the line to this tangent line. So you have to trust me a little bit in that this is something we actually care about that gives us some value. If you have a point, so if like we have the point x, you know, let's not call it x. I don't like that anymore. I'm going to change that to a. we'll work with X later on, but for right now, let's just call it like fix it as a point A. We think of X as being like a whole range of values, and we think of A as being like one fixed value. So let's call this point A, f of A. So we have the point there. So in order to find the equation of the line, really the only thing we're missing is the slope, right? The slope of this line is really the mystery there. So how do we find that slope? And the sort of preview that I gave you is that one way to find or think about what the slope is we're going to pick another value over here. We're going to call that value X. Okay? And we're going to think about how we find the slope of this line, this dashed blue line, which goes through those 2 points. This is not a tangent line. This blue line is called a secant line because it hits the curve twice. But it's kind of close to that red line, and the big advantage is that we can find the slope of that line, right? Because it's 2 points. We know the slope of the 2 points. This top value here is going to be f of x. So I can take f of x minus f of a all over x minus a. Okay. Give me any point you want here, x, and I can calculate the slope of that line just using that formula. Okay. Now the magic here is to say, well, this blue line that I have is not all that close to the red line, right? Like they're sort of close. Could I come up with a better estimate? And the strategy is I definitely could by moving this x value closer to a. Right, and here's where my picture will start to break down a little bit, right? But if I picked a point that was closer to a, all of a sudden I'd have a secant line that is much closer to the true tangent line. Now, even that one is not really that close. Could I make that better? I can imagine you all at home saying, yes, yes, you could make that better. You just have to move this closer, right? And closer and closer and closer. Now, I can't make x actually I can't make x like eat, like consume, like go right to a, because then all of a sudden both the top and the bottom would actually be 0, and I couldn't calculate the slope. We can't find a slope of a single point. It doesn't actually sort of make sense in that sense. But I can make these lines as close to the red line as we want. So let's say that in words here. By letting x get close to a, we can make the slopes of the secant lines get as close to the tangent line slope as we want. Now that's not very formal mathematical writing, but you should recognize that as our limit definition, right? This is actually our limit definition, the same idea. So we can say the same thing by using a limit, and the limit bridges this gap from being really close to equal. Okay, so the limit actually is the bounding value. It's the value that all of these lines are heading towards. We can't actually get there, but that's okay. I can still find what that value is. And that in some sense is the big magical thing about calculus and the limit, is that it can allow us to calculate exactly a sort of unfindable value. There's better ways of saying that, right? But that's the idea. So what this is saying is that the limit as x goes to a of f of x minus f of a over x minus a is equal to the slope of the tangent line at x equals a. That's kind of a big deal. This slope is like a pre-calculus college algebra thing. Not to disparage pre-calculus or college algebra, but been there, right? We've worked with that, done that. This is a calculus idea. This is a new thing. And notice, I think what's interesting here, me as the instructor, is that if you tried to evaluate this limit by putting in a for x, we know that you can't do that in general, but you can see that this becomes f of a minus f of a over a minus a, which is just 0 over 0. And we know that you can't calculate that, right? That's not a number if you try and just plug it in, but its limit may well exist nonetheless, right? We've seen a lot of examples already where if you take the limit of this function, this relationship that doesn't actually exist at that point, you can still calculate what that limit is, right? We call it an indeterminate form. So if we find the slope, if we can calculate what this limit is, we can find the slope. And once we have the slope and the point, we can find the equation of the tangent line, which again is our goal. And you have to trust me a little bit, right? That is a valid goal. Are there questions about this idea? So, this is the danger. Like if you're in class, I could sort of look you in the eye, and students are pretty good at hiding whether they know something or not. But I can still tell usually. But now I don't know. I don't see anybody. I see a lot of names. It doesn't give away a whole lot, right? So there's at least some feedback that it seems, and in some sense it is, right? Like this is like a big idea of calculus, but it does make sense. Like I think when I try and look at math from the outside, there are some ideas that sort of like don't feel like they make sense, you know what I mean? Like our intuition doesn't seem like it works, it does, but this is an idea that I think does sort of match with our intuition. Now the nuts and bolts of it are where we run into a little bit of challenges, right? Like, whoa, how does this actually work when we have some actual functions and we got to find, what those values are. So it turns out there's an alternative definition for this slope of the tangent line that is often easier to use in practice. So I'm gonna give it to you again with just a very slightly different formulation. So we still have our curve here, which we're calling f of x, and I still have my point A, which is where I want to find the slope of that line. And in fact, I still have the same mechanism. I'm going to pick some other point over here. The difference is, rather than calling this other point x and letting x go to a, instead I'm going to call this other point a plus h. So that makes this y value here f of a, and this upper y value here f of a plus h. Now, the mechanism is the same. In order to get the slope between the secant line, we just take the difference in the y values and the difference in the x values. And then to make that equal to the slope of the tangent line, I have to take the limit. And what I want is I want those 2 points to go together. So before, up here, I had to let the x values get closer and closer to a, right? That was the idea. Down here, in order for these 2 points to get together, h is really like the distance between those 2 points. So here, in order to get those points together, I'm going to let h go to 0. And that's really the big advantage of setting it up this way, or one of the advantages setting it up this way, is that it's a limit where the variable is going towards 0. That's nicer than having the limit go towards some number like 2 or 17 or something like that. This one always goes towards 0. And the others, you know, it simplifies a little bit here, right? The plus a and the minus a cancel. So this is also another definition. So m tangent, so that's the slope of the tangent line, is defined as the limit as h goes to 0 of f of a plus h minus f of a all over h. We will see this a lot. This will show up on tests and final exams, and anybody who asks you about calculus, right, will assume that you know this definition, the slope of the tangent line. So these are equivalent, and this will also solve a lot of our problems for us. But this turns out to be typically easier to actually do that limit. And it's the same thing. They're not anything different. I'm just redefining it to make it look a little different when I write it. Let's try one here and see what it does, right? It's one thing to see a definition, something else to see if it actually sort of works. Let's let f of x equal x squared, and let's let a equal 2. So we're looking at that point. That's the tangent line. My goal is to find the slope of that tangent line. So I'm going to use this definition. Don't use other things. This is the definition, the slope of the tangent line. So it's going to be the limit as h goes to 0 of f of a. A is my x value where I'm interested in what's happening, right? It's where this point is. So that's going to be 2 plus h minus f of 2 all over h. Leave that function there so you can see it. So f of 2 plus h, this is my function. So 2 plus h squared minus f of 2, right, which is 2 squared, all over h. So just some algebra here. Remember to FOIL that out. Two squared is 4, all over h. Notice, like in the beginning here, if I put in h equals 0, I'm going to get 0 over 0. That's not like a bad approach with limits, but just like the other definition, if you look at this one, if you put in 0, you're going to get f of a minus f of a over 0. You're going to get 0 over 0 automatically every time. So these limits are always going to be an indeterminate form. So you don't even bother plugging it in. You start right away with trying to simplify it and reduce it, which is what we do with indeterminate form problems. So notice the +4 and the -4 cancel. This one I don't really have to do any factoring, right? I can divide both of those by h. And that's, it turns out to be the secret to changing this indeterminate form into something I can calculate. So now that I've canceled, right, the h from both of those with the h in the bottom, now I can use direct substitution to calculate that limit, right? And that's what we talked about last week. This function and this function are not identical because this function doesn't exist at 0 and this function does. But their limits are going to be equal to one another because we don't care actually what's happening at 0 for the limit. These functions are the same everywhere else. As h goes to 0, this becomes 4, right? The limit of 4 is 4. And it's a little hard to tell from my decidedly mediocre graph, but it certainly would seem reasonable that the slope of this line might be something along the lines of 4, right? The rise over run. It's certainly a fairly large positive value, and it turns out that matches exactly with what we calculated. This, what you'll see, and I'm going to stop here kind of momentarily. We'll continue talking about derivatives a little bit, although we've really gotten through the main portion of everything. But this idea, it turns out to be the backbone of much of what we do in the rest of the course. We will learn some shortcuts for sort of calculating these, but this is how they work. They are limits. You want to make a big distinction here between the limit of the function and the slope of the tangent line. And maybe this was a bad example because it sort of feels that the numbers are kind of the same, but it's not, they're not equal to one another. So how can I best? Just trying to think of the if there's another example or a sort of visual way of just verifying these two things are different. Well, here, yeah, I think I've got an idea. Let's try this one. So here are two questions. What is the limit as x goes to 1 of f of x? And what is, well, I should have made a definition here first. Sorry, I got a little off track with trying to, was worried about you confusing things, and I probably haven't helped that. But before I solve this problem, let me just make a quick definition. It's a pain to write the slope of the tangent line at 2. Like, I don't want to have to write that every time. Nobody wants to have to write that every time. We need a little shortcut. And so the shortcut we use is we're going to call this f prime of a, and this is called the derivative. And all it is it's exactly this. It's the limit as h goes to 0 f of a plus h minus f of a all over h. Sorry if I ran out of room there. It's exactly the slope of the tangent line. And this part is the same. I'm just naming it differently because it's much more convenient, and it's going to help us think about this derivative as a function in its own right. Okay. And I kind of need that because I couldn't even really ask my question very efficiently without having this notation. So my question here is, first of all, what is the limit as x goes to 1 of f of x? And secondly, what is f prime of 1? What is the derivative of f at 1, which is the same as the slope of the tangent line to the function at x equals 1? That's the thing I didn't want to write all the way out. These are both involving limits, right? But they're talking about really two very different things, okay? The top line is saying, what is the function doing as x gets close to 1? And I can see here as the x values get close to 1 from both sides, the function is a nice continuous function. It's just approaching this y value of 1, okay? This is a different question. This is saying, what is the derivative of the function at 1? The derivative is the limit as h goes to 0, f of 1 plus h minus f of 1 all over h. That's a limit, and it's involving the function, but this limit is calculating something different. This is calculating the slope of the tangent line. So if I drew a line that just sort of mirrored that function right at that point, right? Imagine you zoom right in, the line and the function look very similar. That's what the tangent line is. This here, f prime of 1, is going to be 0 because this function is flat. Okay, so I think sometimes in the beginning when students are a little less familiar with the idea of the limit, they sort of blend these two ideas together, and we don't want to do that. The limit is a tool that is helping us find this value of the derivative, right? This f prime, which is, we know, the slope of the tangent line. Slope of the tangent line to f of x at x equal 1. Okay. Questions about that? The focus of this little time was more on the sort of intuitive idea of what that derivative is and the definitions. I think you'll find in the homework you'll be actually calculating more of these, right? Finding some actual values and some limits. But you've got to understand what you're trying to do, and of course what it's asking you to do as well. Okay. I will let you go. If you have some additional questions, you can certainly stick around and ask those. Otherwise, hopefully I'll see some of you on Thursday. And as always, I'll record and post this to D2L. So if you want to go back over any of the examples, or if you miss a day for some reason, you know, I would encourage you to take a look and skim through them as well.
Thank you.
Thank you.
You're welcome. Thank you guys. Take care. Enjoy the